Okay, good afternoon, everybody. So, quick review about random variables. So, we said random experiment is an experiment that whose outcome is random and you don't know in advance. Like rolling a dice, producing a part, you don't know if the part is going to be conforming or non-conforming. And it could be, the random variable is basically is a variable associated with outcome of your random experiment and can be categorized in two classes. One is discrete and the other one is continuous. If basically we want to model a discrete, basically random variable, we need to use discrete distributions or probability mass functions. And the probability mass functions have two properties. They should be non-negative, and the summation should be over the range should be 1. And we said point probabilities are basically for non-integer points. If we say the range is integer, gonna be 0, as you can see. So let's say this is the first integer. We have a probability associated with that. But for the second one also, but in between, you can see there is no probability. Probability is equal to 0 for non-integer points. And we had one example. And then we said for continuous, where's the continuous? Oh, the CDF first. Then we introduced the concept of CDF, or cumulative distribution function, which was simply probability of x less than equal to a, and for calculating that we need to add up the PMF function from the lower bound up to a, including a. Okay, and CDF has some properties, always between 0 and 1, monotone function, and if you want to calculate probability of x between a and b is inclusive, then you need to basically simply just find CDF of B and subtract CDF of A from that one. Similarly, we can find the probability of this inequality where both of them are inclusive, and this is going to be the equation. Okay. For continuous distribution, we are using probability distribution function. Probability density function. And the other one was probability mass function. Just different terms. For discrete probability mass function, for continuous probability density function. And as you can see again, non-negativity condition is there. Instead of having summation, we have integral. And for a range, we can find probability. For example, probability of x between a and b is simply integral of the PDF function between a and b. And we know that point probabilities are always equal to 0. There is no point probabilities. So it doesn't mean that f of a, let's say, f of x is something like this for exponential distribution. Okay? When we say probability of x equal to a is 0, it doesn't mean f of a is equal to 0. Definitely, if you put, let's say, lambda is equal to 2, if you plug in, if x is equal to 2, or a is 2, then if you put 2 here, you get a number. But this number is not probability. It's just the value of PDF function. Probability is always defined over a range. And point probability for continuous distribution is equal to 0. Okay, for continuous distributions. Any questions? And this is again CDF function, the same basically definition, probability of x less than equal to a. Instead of summation, we have integral. That's it. One example. Did I cover this example on Friday or not? This is new? Okay, I guess so. Actually, very similar example. You have a k here, and it says, the first part says, find the appropriate value of k. Okay? Any idea how we can find k here? Any suggestions? Exactly. So we use the property or definition of PDF function that f of x, if you integrate over the whole range, then this integration should be equal to 1. Okay? So in this case, since the x is greater than or equal to 0, so we'll start from 0 to infinity and to e to the power of minus kx dx. And this should be equal to 1. We do integration, which gives us this guy, x from 0 to infinity. This should be equal to 1. And if you plug in infinity here, it would be what? 0 and minus 1 equal to 1. Therefore, your k is equal to 2. Okay? That easy. Is it clear? Any questions? Cannot see that over there. Okay. Second part says find the probability of x greater than 0.5. So what we need to do, again, integrate from 0.5, because it says greater than 0.5 up to infinity of this PDF function, and we basically replace k with 2, because we already know what k is. d of x, okay? And it's simple integration. If you do that, that's going to be something like this. Or 0.5, doesn't matter. Minus 2 times 0.5, which is e to the power of minus 1. Okay? Any questions?
Is that the same as saying 1 minus the integral from 0 to 0.5?
Exactly. Yeah. So, or you can use the definition of CDF function. So this guy is the same as 1 minus f of 0.5, which is 1 minus probability of x less than 0.5, less than equal 0.5. It doesn't really matter if you have equality here or don't, because it's continuous distribution and point probabilities are equal to 0. By the way, anybody knows what this distribution is called? What? Yeah. I'm hearing something, but...
Exponential.
Exponential. Yeah. It's called exponential distribution. Any questions? Okay. So I give you just a minute or so to try to solve this example. Simple. We have a quality characteristics, and let's say it's length of a product, okay, or part. And a specification limit says it should be less than 12.5, okay? What is the percentage of non-conforming parts? Non-conforming means it doesn't satisfy basically a specification. It doesn't meet a specification. I'll give you a minute or two to see if we can solve it. Fairly simple example. I walk around. If you have any questions, ask me, okay? Okay. Anybody got answer? A, B, C? Anybody? B, C, A, B? Nobody really? A? How many got A? 2? 2. Okay. So let's see. So we want to find the percentage of non-conforming items. Okay. So standard says x less than 12.5, we have conforming or a good product, and x greater than 12.5, we have non-conforming. Okay? So we want to find probability of producing a non-conforming part, which is this guy. It doesn't matter if you put equality or not, because we are calculating probabilities. Okay? And it's continuous distribution, so it doesn't really matter. So we need to integrate PDF function from 12.5 to upper bound. Okay, so the PDF function that we have, if you look at the PDF function here, it's a piecewise PDF function. And depending on the range that you are doing the integration, you need to either find this guy or this guy. 12.5 belongs to this range, okay, the bottom range. Therefore, I use the bottom equation here. Does it make sense? So 12.5 up to 12.75, which is the upper range. And if I do that, it's 12.75 minus x dx. And if you do the calculation, it's going to be 1.25. Actually, 0.125. I'm sorry?
And 12.5 not greater than, that's what the question says.
It says non-conforming. Yeah. So if it is conforming, it's less than 12.5.
Gotcha.
It says non-conforming is, yeah. Any questions? And I assume that this integration is not the big deal, right? So I just wrote down the answer. Any questions? Are we good here? So what if we want to calculate this probability? Let's say 12 point, let's see, yeah, 12.5, okay? If we wanted to calculate this probability, we would have basically, we should integrate from both equations, okay? So we should integrate both equations. The first one is from 12, because 12 belongs to this range, and 12.5 belongs to this range. So what we need to do, 12 to 12.25, we do the integration with this equation. And from 12.25 to 12.5, we do this integration. Okay? That's another example that we use both equations depending on the range. Is it clear? I'm going to block. Any questions? Okay. So, you remember we had like sample mean, population mean. You remember, and the difference between these two? Okay? And there is another way to get the population mean. One way of finding population mean is to observe all population members. Okay? If you have this information, then you can find population mean. In some cases, it's not possible. Okay? Another way for finding population mean is if you know the distribution, then you can find, if you know the PDF or the PMF or PDF, you can find population mean, which is mu. It's also known as expected value. So for discrete random variables, is just multiplying x and by basically PMF function and summation over the range. For continuous random variable, you just replace summation with basically integral. We also have another definition, which is called moments. So this moment are used later on for estimation as well. Mean shows the center of your distribution. Okay, like normal distribution. Mean shows the center. Those moments are related to location and shape. Okay, location, shape, and also the spread. Okay, and so depending on what moment are you looking for or are you interested in calculating, we change R. So the first moment is the same as what? No, the first moment, mean. The second moment is related to variance. The third moment is related to, somebody said here, skewness, and the fourth moment to kurtosis. Okay? And so this is basically the equation for moments. And here is the definition of the variance. So the variance is the second moment around mean. So this is the second moment. Let's say for basically continuous distribution is this guy over x. And this is second moment around mean. Okay? This is called variance. Variance of x or sigma squared, which is this guy. Okay? There is another equation for finding variance. Is the second moment minus first moment squared. Okay? Second moment minus first moment squared. These are exactly the same, so we can show that. It's going to be easy. Maybe in your homework you need to show that. Maybe. Okay. Any questions? Is it clear? So basically you can show that this guy is exactly the same as this guy here. We're good here? Okay. Now, a couple of examples. The first one is discrete, the other one is continuous. Find expected value or mean. I'll do the first one, you do the second one. Okay? For part A is discrete. We know that the expected value, it says mean and variance. Okay. Is let's call this I. This is the equation for expected value, which is simple. So we have, or let me call it A to be consistent with what we have on the slides. So A equal to 0 times corresponding probability is what? Is 5 over 6 squared. So it's 0 times 5 over 6 squared. What is the next one? 1 multiplied by 2 multiplied by 5 over 6. So this is the number A, and this is the probability associated with the number. And the last one, number is 2, and corresponding probability is 1 over 6 squared. If you do the math, that would be 1 over 3. Yeah, I hope so. Always double check my calculations. Okay? How about the variance? Variance of x is A minus mu times P of A over A. In this case, 0 minus mu is what? This is mu. 1 over 3 times the corresponding probability, which is this guy, plus 1 minus 1 over 3. Oh yeah, squared. Thank you. That should be, oops, this one. Thank you. Corresponding probability is this guy. And the last one is 2 minus mu squared times the probability. Okay? Anybody can tell me what this number is without solving it? You can? Nobody? I can. I solved it before. That's why. How about this guy? Maybe. Oh. No. Now it's better. Yeah. But double check. Any questions? Okay. If there is no question, let's start working on part B. So exam time is limited between 0 and 1 hour, and students basically finish the exam time in a random fashion, all right? Finish the exam in a random fashion. And it's explained by this PDF function. And the question is, what is the average of this random variable? And what is the variance of this random variable? I'll give you a couple of minutes. Oh, no. So that's actually a good point. So your random variable is x, okay? And this is, alpha is the parameter and it's multiplied, okay? So alpha multiplied by, yeah, that's not good actually. Alpha multiplied by x and again to the power of alpha minus 1. Good point. So it would have been better if I wrote it like this. So your f of x is alpha x alpha minus 1. Yeah. So expected value definitely should be a function of what? Alpha. So any answer? 1 over alpha? Let's see. So the expected value would be x times f of x. We know that x is between 0 and 1. And so integrate from 0 to 1. D of x. So 0 to 1, alpha x, alpha minus 1 d of x. And this would be alpha, or x to the power of alpha. That's easy. Oh, yeah, I dropped. That's why I'm saying always double check what I do. This times x d of x, which would be alpha over alpha plus 1. It's x alpha. Yeah. It's alpha x to the power of alpha dx, the integration of this guy. And that would be, yeah, I was right. Plus 1 from 0 to 1. And that would be this guy. Okay? Does that make sense? So actually, 1 to the 0 to the power of alpha plus 1, which is this guy. This is 1. Okay, any questions? Go ahead.
Expected value, just like a definition?
Yeah, that's the definition, exactly. So what you do for any distribution, it doesn't depend on the type of distribution. For any distribution, that's the definition. Okay? Okay, how about the variance? So for variance, I'm going to use the second equation this time. Do you remember variance of x is expected value of x squared, or I have it right here. So the second moment minus the first moment squared. Okay? So I already know the first moment, or mu. I need to find the second moment, which is the expected value of x squared. And based on definition, it's x squared times f of x, which is alpha x alpha minus 1, d of x from 0 to 1. And this is alpha x alpha plus 1, yes. dx to 1. And that one would be from 1 to 0, which would be this guy. Okay? Is it clear? Any questions? And therefore, our variance would be this alpha over alpha 2, alpha plus 2, minus alpha over alpha plus 1 squared. This part is the expected value. I got it right here. And the first part is right here. So I just use the definition for finding variance. Any questions? Okay, good. So there are some useful results. That's actually we use a lot in probability and statistics. So the expected value of a constant plus a random variable is that constant plus expected value of that random variable. And multiplication is the same thing. For the variance is interesting. If you have a constant, this a is not a random variable. It's a constant. It's deterministic. Okay? So you know that variance of a deterministic variable is what? Is 0. Okay? So if you don't have, if the variable is deterministic, okay, it's just one variable. It doesn't change. So it doesn't have any variance. So the variance is equal to 0. Okay? Therefore, variance of a plus x is just variance of x. Okay? Exactly, the variance doesn't change. That's a very good point. So that's exactly, if this is the distribution, this is expected value of x, then if you want to find expected value of x plus a, it means you shift the distribution. Let's say this is a. Okay? But the variance doesn't change. You shift the distribution, and that's basically because of the first property, but the variance doesn't change because of this property. But if you multiply it with a constant, then it's going to change. And with the rate of a squared. See, so a times x is going to be a squared. Okay, if I have some random variables, that's also important. We use it a lot. Expected value of a linear combination of random variables is the linear combination, the same linear combination of expected values. You see that? So expected value of the linear combination is just the same linear combination of expected values. There is no assumption. It's always true. Okay? However, for the variance, this is not always true. So the variance of a linear combination, as you can see, is the linear combination of variance with a squared coefficient, as you can see, because of this property, with a squared coefficient, if and only if x's or basically random variables are mutually independent. There is no correlation. Okay? So for example, if x1 changes, it doesn't affect the value of x2. Okay? Or when x2 changes, it doesn't affect value of x3. So if for this to be true, we need to have mutual independency. Does it make sense? So if I have this guy, what is this guy? Is expected value of x1 minus expected value of x2. If I want to calculate the variance of x1 minus x2, what is it? And x1 and x2 are independent. It would be what? Variance of x1. That's going to be plus. Why? Because of the very last property that we had here. Okay? So it says coefficient should be a squared. So what is the coefficient of this guy? Is 1 squared is going to be 1. What is the coefficient of this guy? Is negative 1 squared going to be positive 1. So it's basically variance of x1 plus this guy, which is the same. Same thing. Okay? Any questions? use this a lot. Go ahead.
How would you deal with the variance for that situation?
If they are dependent? Okay. So let's say, I want to give you a simple equation for that. Variance of x1 plus x2. Okay? And if they are dependent, there is some covariance between these two. So it's going to be variance of x1 plus variance of x2 plus 2 covariance of x1 and x2. I will teach you covariance later on when we are talking about basically the regression and relationship of two variables, what covariance is and how we can calculate that. But this is the equation. So what you have one more element, which is the covariance. And the covariance captures the relationship of two random variables or more than that. Okay? Any other questions? Okay. So let me review some discrete distributions. If you had any probability courses before, probably you've seen these distributions. These are well-known distributions, or I would say some events. Okay, some events in the nature or in factory or in your field of study can be modeled through these well-known distributions. Okay, we start with discrete distributions. The very first one is Bernoulli distribution. And if your random experiment has only two possible outcomes, okay, then you have a Bernoulli trial. How you can model a Bernoulli trial? Using Bernoulli distribution. Okay, let's say you're tossing a coin. Okay, what happened? It could be either head or tail. Okay, so if it is a fair coin, then you have the probability going to be half. Otherwise, it could be p in general. So what we have, the application of Bernoulli distribution, as I said, to model the outcome of a Bernoulli trial. And we define one of the outcome as success and the other one as failure. Okay, for example, we can say we bet on the tail, and tail would be success. Okay, and here is one example, the outcome of inspecting part quality. You have a part, you inspect that part, either it works or doesn't work, conforming, non-conforming. So, and here is very interesting. Usually we define success as when the part doesn't work. Okay? So in quality control, if part doesn't work, we call it success. Okay? And the reason is because we are interested in modeling and analyzing the rate of failure and the rate of defective. That's why we define success as basically producing a defective item. Okay? That's just a convention. Probability mass function. So with probability of p, you observe your outcome gonna be success. With probability of 1 minus p would be failure. Okay? So your probability mass function is simply either p or 1 minus p. If a is 0, if a is 1, if a is equal to 0. Okay? So if you combine these two, this would be your probability mass function, which has both at the same time, instead of having piecewise. Okay? This is the expected value, and this is the variance. Okay? Any questions? Is it clear? Binomial distributions. So what if I have more than one Bernoulli distributions? Not only I'm inspecting this part, I have 10 of these parts or 100 of these parts and inspecting them. Okay? Then I want to find what would be the probability of producing 10 defective or non-conforming parts out of this 100. Okay? So you have more than basically one Bernoulli distributions. Then you can model, you can use binomial to model that. As you can see, to model the number of successes in n independent Bernoulli trials. So somebody can tell me what independency basically mean here. Go ahead.
By any of the other outcomes?
That's correct. So in the case of inspection, what does it mean? Exactly. If you produce one bad part, it doesn't affect the quality of the previous nor the next one. Okay? They are independent. In this case, one example, as I said, number of non-conforming parts in a random sample of parts of size n. This is the probability mass function. Probably some of you have seen this before. This is n choose x, and this part is for modeling success and failure. That's the expected value, and that's the variance. And you can see, do you remember the example I gave you just a few minutes ago about rolling dice twice and the number of 6 that you observe? If I go back very quickly, you see? So what is this distribution? It's binomial. And what is n here in this case? Is it 6 or 2? It's 2 because I am doing 2 Bernoulli trials. The first one is, actually, I'm doing rolling dice twice. Okay? And your P is what? It's probability of success. Probability of observing 6, which is 1 over 6. Okay? So in this case, your expected value would be NP, which is this guy. And your variance was NP1 minus P, which is this guy, which is 5 over 18. And that's why I ask, anybody can tell me without solving that or calculating that long summation, what would be mean and variance. That's exactly how I did it. And I did a drawing at the beginning. But I fixed it. Okay? Any questions? Is it clear? Okay. That's binomial distribution. Very interesting fact. You know that n independent Bernoulli trials gives you binomial. Therefore, if you have some Bernoulli random variables, summation of these random variables gives you binomial distributions. Here is one example. Let's say x1 up to xn, all of them are Bernoulli with parameter p. Okay? You define y as x1 plus x2 up to xn. Then your y follows a binomial distribution with n and p. The most important assumption here is independency. So x's, those Bernoulli trials should be independent. Any questions? We have one example, but I don't think we have time for that example. I continue on, try to solve this example at home, but we continue on Friday.